Welcome to a new video about analog filter design. In this example, we will look at the Chebyshev response active bandpass filter design. We'll use the Geffe algorithm as we have done for the butterword response in the previous example. We will see how we can generate a sixth order filter, which is shown here. And we'll of course simulate that in the Tina TI SPICE simulation also. We'll first show our calculation step by step and also verify this in SPICE simulations. We have the following design objective. We like to design a Chebyshev response, as said before, an active bandpass filter. Specifications are shown here. So we like to have the maximum passband ripple of 0.5 dB. That is the ripple for our Chebyshev response. The minimum step band attenuation requires 30 dB and an effective midband gain is 0 dB. So we have unity gain at midband. The lower and the upper passband frequencies are shown here, 2 and 3 kHz. The lower and the upper passband frequencies are 1 and 6 kHz here. Okay, let's look at our solutions. The first calculation is we start with the passband bandwidth, center frequency, and also the quality factor for our final bandpass filter design. The passband bandwidth is the upper minus the lower passband frequency in radians, and that's given by this expression. We do then 3 minus 2 kHz, and it will give us 1 kHz or 2 pi times 1 kHz here. Okay, that's for the passband bandwidth. The center frequency is the geometric mean of the upper and the lower passband frequency, again in radians, and that will be then calculated like so, and that will result in 15,391 radians per second. The quality factor is the omega center over the omega bandwidth, that is shown here. That will give us here 2.4495. Okay, now this is an information we will use later. Step 2 is the normalized passband frequency, normalized stopband frequency of the prototype low pass filter. As we said in the previous examples, we start always with the design of a low pass filter, and then we will transform that to the bandpass filter. This is the normalized passband frequency. This is normally always 1, so I will just show you that the original formula also. So you'll see here again a difference between the upper and the lower, and then again the passband bandwidth. That will result in 1. The next one is the capital letter omega sub s. That is given by this, so the upper and the lower stopband frequencies divided by the omega bandwidth. You will have this one, which is then 5. By the way, it says here bandwidth, but this is not necessarily bandwidth, because it doesn't have to be 3 dB lower than the midband gain. Okay, that's for the prototype low pass filter. Now the filter order, one of the important steps for the prototype low pass filter, we would like to calculate that. First we go to the epsilon p, which is related to A max, which is 0.5, so that we'll substitute it here. You will get here 0.3493. Epsilon s similar to the first one, then we will use the A minimum stopband attenuation. That will give us here 31.607. Now taking this together in the formula of the Chebyshev response, which uses this expression, we have the epsilon s required epsilon p, and also again from step 2 the normalized stopband frequency and normalized passband frequency. Now when you substitute the values here, you get the 2.27 approximately. So we need to have an integer order, so we need to go up to n3. Now you see here that this value is actually closer to 2 than 3. So our final performance will be much better than what we have here. If this, for example, was 2.9, for example, we will maybe get very close to a little bit higher than the minimum stopband attenuation. So I can already estimate that from this answer. Step 4 is a normalized Chebyshev pulse of the prototype low pass filter, as we have done also in the previous example for the butterword pulse. We also need the Chebyshev pulse. Now the expression for the normalized Chebyshev pulse are given here. You see here the sine and the cosine, actually, as we have seen in the butterword, but you have now an extra term, sine hyperbolicus, and also the cosine hyperbolicus. So we have an extra term, and we also have a parameter a here, so we need to calculate that also. What is a? Now k, let's start with the k here. The index k is the pole number. In this case we have n is 3, which is our filter order, so that's also in the formula. And a here is given by this expression. You see here inverse sine hyperbolicus, but also the epsilon p we have determined in step 3. This is just expressions or numbers, so we just calculate that and we get here using the filter order, also the epsilon as 0.5914. Now when you substitute that in here, you can then calculate for each pole the value. Okay, now let's do that then, because we have a third order filter, or for a prototype low pass filter and a 3, we have one complex conjugate pole pair and one real pole. So that is in total 3 poles. So the poles are given by this. So you have K1 and K3. Those are the complex conjugate pole pairs. For K2, you substitute again similar to the K1 and K3. Here the formula for K2, you get now a real pole, as said before, of minus 0.6265. Okay, these are important values we need to use later. So let's bring them here, and also the center frequency we have determined, and also the Q factor, the quality factor of our bandpass filter we require. Okay, we now assign Geffe poles, so that's the algorithm we need to use in this example for the values we have determined for our poles. So this is given by P sub G. So the real part and the imaginary part of each pole will be assigned to the Geffe pole parameters, which forms then the Geffe pole. So we will show that, how that works. So the Geffe pole again is given by P sub G, and that is given by the sigma, capital letter sigma, and the capital letter omega. And those are found from the real part and the imaginary part from our poles. That's also shown here. So this is the real and the imaginary value for the Geffe poles. So index G, which refers to the stage number, will be the final bandpass filter to be designed. So if you have 3 stages, we will have P1, P2 and P3 for the Geffe poles. Okay, since we have 3 poles, we have 3 stages for the final bandpass filter. Each stage forms a second order filter, therefore the final bandpass filter will be 3 stages times second order will be a 6th order, so 3 times 2. Note, there's an important note here. Unlike the butterworth response design of a bandpass filter using the Geffe algorithm, we do not scale the poles of the Chebyshev response for the bandpass filter design using Geffe algorithm. So there was a step after this one where we scale the butterworth response poles. We don't do that here for the Chebyshev response. That's not required. The bandpass filter stage 1, we start with that. That is then G is equal to 1. We start with the real pole P2, this one. For that, since there's no imaginary part, the capital letter sigma 1, because we refer to the stage, is that 0.6265. So we only take the real value as a positive, and there is no imaginary value, so that will be then capital letter omega 1 is 0. Now for the stage 2, for the bandpass filter, we look at the P1, and since it's a stage 2, we will then assign this capital letter sigma as 2. This is just the positive part of the real value of this pole, and also the capital letter sigma 2 will be then the imaginary part. In a similar form for the stage 3, that's actually shows, so those are exact same actually. So P1, P3 are the complex conjugate pole pairs, complex pole pairs, and we have the real pole here, P2. Okay, now we have the necessary information, and we can now look at the Geffe parameters for each bandpass filter stage. First, we start with the stage 1. Okay, now this is the formula we start with the Geffe algorithm. So C1 is equal to that one. Now we know what we have, so these are the required parameters. We already have that from here. So we can say this is then equal to 0.3925. Okay, we continue with the D1. From this formula, again, we need the bandpass filter quality factors. And again, you substitute the values, you get here 0.5115. The E1, similar form, we already have the C1, we know the quality factor of the bandpass filter. There's just some process we need to carry out, and we have here the value for E1. We have also G1 here from this formula, that will give us 3.9346. The quality factor for stage 1, Q1 is given by this expression. We have E1, we have the G1, and we have T1 from the previous calculation, and it will result in 3.9101. Now moving on for the next parameter, K1, that's calculated using this one, will end up exactly to 1. W1 will be, in this case, also exactly 1. And then the center frequency for our first stage, omega center 1, is related to W1 times the center frequency we have determined earlier, and that will result in 15,391 radians per second. Stage 2, and we do actually the similar calculations. Now we of course have a complex conjugate pole pair or complex pole pairs. So, and those are actually exact same, so they will have exact same poles. They will be exact same in most parameters. Only change is the center frequency. So they also have the same quality factors. So the calculation for the stage 2 and 3 together is actually this one. So this is also valid for stage 3. So C2 here, which is given for stage 2, which is also the same for stage 3. So you see here that we have an imaginary part that's shown here. It was not the case for the stage 1. Now we have this for C2, for D2 here, and for E2 here. So just follow the procedure and substitute the values from the parameters here and also what we have calculated. Then we have the G2. The Q2, which is the quality factor of stage 2, is given by this expression. We have the D2, E2, and the G2, which we require here, and it will result in 7.9891. This is also the quality factor of stage 3. So moving on to the other parameter, which is K2, which is in this case 1.0216. W2 is given by this expression. When you substitute values, you get here 1.2306. Now the center frequency 2, so the omega center frequency 2 for the stage 2 is given by this expression, which is W2 times the omega center, which will result in this case, 18,940 radians per second. Now we said already that Q2 is equal to Q3, so they have the same quality factor, and also W3 is equal to W2, that's also equal to each other. The only difference is the omega center, so the center frequency, that will then result in this equation where you have now the W3 divided. So you have now 12,506 radians per second for our third stage. We also need to calculate the total midband gain. Now the total midband gain is required in order to also get to the effective midband gain of 0 dB. So the gain of the bandpass filter, the center frequency, is called the midband gain. And for each stage there is a midband gain, and that is given by this expression where you see again the quality factor, the center frequency of each stage, and also the center frequency for the bandpass filter in total. So the total midband gain of the bandpass filter is given as follows, where G is the bandpass filter stage and the N here is the number of stages we have. So in this case we have G is equal to 1, 2 and 3. So we have here 3 stages which needs to be multiplied. This is a product symbol in mathematics. Then we have the following midband gains. Now for stage 1 we just look at the quality factor, center frequency, and also the center frequency we have in general here. So the center frequency of the specific stage, the quality factor of the specific stage, and we have this one. We can also do that for the stage 2 in a simple form, just change the indexes, and stage 3. We will see that the AM2 for stage 2 and the AM for stage 3 will be exactly the same. These are the values we have determined for the quality factor, center frequency for each stage. You can see that here, and these are for the quality factor exact same, only the center frequencies are different for stage 2 and 3. Now let's calculate the stage 1 first. You see here the values substituted. You get here 30.58. And for AM2 we can calculate that using the quality factor and also the other parameters. That will give us 36.62 approximately. Now when you do that here, although this is different here, they get the exact same AM3. So we can say in the future, if you do these calculations to shorten your calculation, you can say AM2 is equal to AM3 if there are complex pole pairs. So the total midband gain is the product of this AM1, AM2 and AM3 as set here in the expression. So it will give us here approximately 40,998, almost 41,000, and it will approximately be in dBs, 92.26 dB. Okay, now we need to, of course, use that to adjust your midband gain to 0 dB. It will be done later. First, we have the circuit realization. We need to cascade 3 second order bandpass filter circuits to create the 6th order bandpass filter. So there will be here a multiple feedback. You see the feedback here, 1. the inner feedback, and another feedback here, the outer feedback. This is now the multiple feedback circuit, where you see the normalized values for the capacitors, CC, R2, and R1 and R2. Okay, now we select a value for the capacitor. In this case, this is convenient because that is harder to find compared to the resistor value. So we just take here 100 nanofarads, but any other value will do. And we will now calculate the rest of the unknowns for each stage. Now the formulas for the denormalized component values, so not the normalized but denormalized, the scaled component values are given by this expression. You see here the G again, that's the stage number. The M here refers to the magnitude scaling factor here, and this again similar to that one. The Kf is here the frequency scaling factor, and Km is the magnitude scaling factor. Now let's start with the denormalized component values for the stage 1. Q1 we know that is 3.91 approximately, C1 we have selected, and the Kf1, which is for the first stage, will be just the center frequency of the first stage, which is the 15,391 radians per second. That is shown here. And now we can calculate the others, which is then Km1. We actually use this formula, or that formula, it doesn't matter, and then go here, because since the C1 is selected, we can go to the Km1, because the magnitude scaling factor is not known yet. When you have calculated that, you can calculate now the R1 for the first stage and R2 for the first stage. That is given here. In a similar case for stage 2, G2, so everything actually changes, just the index to, you look at the table, you look actually what you need to calculate again, similar to this one, and these are the results. And for stage 3, you have this one. So we have now the components for each stage also. So those are now summarized here. So stage 1, stage 2, stage 3, and we have the R1, R2, and the capacitors, but these are all 100 nanofarads we have selected. And you have these values. So we need to find use these values in 3 times this circuit in cascade. Okay, there is one step we need to do, which is then going to the effective mid-band gain. So we need to make a gain adjustment circuit. So we know that we had almost 41,000 as a gain, but you know we need 1, so we need to go down. So how do we do that? Now the required effective mid-band gain is set as 0 dB or 1. We have this total mid-band gain, and we need to find a way to get this value, huge value, to 1. Now we can do that by attenuating that, and the circuit is shown here. So we can go in here at node A and then measure at node B by using the voltage divider circuit here. Now we can then say that the HM, which is our required effective mid-band gain, over the AM we have, will be then this. Now, in order to calculate the Ry and Rx, we need to actually have another equation, so we need to select one of these. So we just select or take Ry as 1 kilo ohm, another value will do also, and we will then calculate that Rx since we have the rest. So that will be then, this will give you 40.998 or 41 mega ohm approximately. Okay, that is the final result for the components. And these are the component values for the multiple feedback circuit. Now design circuit is shown here, and that is also what we have drawing in the SPICE simulator. You see here the first stage, the second stage, the third stage, and also the attenuation circuit here. Okay, now let's look at the simulation results. This is the body plot, only the gain, where you see the ripple also in the passband. That is really the characteristic of a Chebyshev. It was flat actually for the Bellwether response, for example. Let's go one by one. This is the circuit. You see here the center frequency, which is 2.45 kilohertz, but we have calculated, as remember, the center frequency was in the radians per second, 15,391. And if you now do that divided by 2 pi to get this in hertz, you get also 2.45 kilohertz. So that is indeed correct. The gain at 2 kilohertz, it is here minus 0.5 dB. The gain at the center frequency is also 0 dB, so that means 0 dB here going down by 0.5 dB, which is the ripple we wanted at that 2 kilohertz. So that's exactly as we wanted. Now going down again from here and then looking at 3 kilohertz, we see that we also have a gain of minus 0.5 dB, again as we wanted, so the maximum passable ripple is also achieved. Looking at the two other parameters, which are the stop band attenuation, as set in the calculations, we had almost let's say 3 as the n, we round it up to n is 3 as an integer. So I said in the discussion that I estimate that the performance of the final design will be much better than the required here. So we require here stop band attenuation of 30 dB. If I look at my stop band frequency 1 kHz, I expect that this is much higher than what we require, and it's also what we see here. It is almost minus 44.6 dB, which is way higher than we wanted. So that is of course fine, because this is minimum. So this is also as expected. So that not the value maybe, but this is higher. And the 6 kHz, also another parameter, you see the exact same attenuation. So we can say all the specifications are met, so we have achieved our goal. Alright, this was our example concerning the Chebyshev response active bandpass filter. We have used the Geffe algorithm to calculate the necessary values, the parameters, and also created our circuit using multiple feedback circuit elements. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.